Armstrong. Okay. I'd like to talk about some discussions that I had with Sarah, Tassos, Anne-Christine, Raquel, and Scott when we were preparing our last paper. So this is a teaser for a work in progress. So generally, inflation is known to solve many problems of the old Big Bang theory, and it also produces the primordial perturbations. And now inflation serves as a very nice illustration of the relation between theory and experiment. So theory wants to be tested by experiment, but on the other hand, experiment, or for that matter observations, need theory to be interpreted, and eventually from a theorist's point of view, all that experiments and observations are for is to determine the values of the parameters of the theory. Let me now just give you a brief sketch of the multi-field inflationary setups, of which I'm going to consider two-field models. So in such models, the trajectory, the inflationary trajectory in the field space can be curved, and it is convenient to consider perturbations along the trajectory and those orthogonal to the trajectory. And those along the trajectory will eventually become the curvature perturbations that we see, and those orthogonal can be called isocurvature perturbations because they will be such perturbations if they survive reheating. So it is known for a long time that on super Hubble scales, when there is a turn in the inflationary trajectory, the isocurvature perturbations can feed the curvature perturbations. And one has to remember that since these are two independent quantum degrees of freedom far within the Hubble radius, of course, the primordial curvature perturbations and those inherited from isocurvature perturbations should be added in quadratures as independent perturbations should. Now, the story becomes a little bit more complex if one goes to non-trivial metric on the field space. But the basic notions stay the same. Basically, instead of a turning trajectory, we should say that the trajectory deviates from a geodesic line. And there was quite a big activity on such models in the last couple of years. However, I would like to go back to the case of canonical kinetic terms. And let me give you an analogy. So from Psychology 101, we know that at least in humans, violent events in the past can have far-reaching and long-lasting consequences. So I'm going to ask a question. Are scalar fields like humans? By a violent event, I'm going to mean a very specific one, and that is that let's consider the largest mode that we can see in the CMB, and let's enjoy the possibility that this mode spent a little bit of time when it was sub-Hubble. So then we have a turn in the trajectory when the perturbation was below the horizon, and the turn is by the amount of delta theta. So now the question is, can such an event which happened when the perturbations was in the quantum realm within the Hubble radius, could this leave some imprints in the power spectrum of the curvature perturbations that we see today? So there are many answers in the literature. So I'll give you some of them. So there is a prediction for sinusoidal oscillations or a shift in the power spectrum, or that nothing really happens. I'd like to remind you that we are considering the limit of a really large K. So of course, because these three proposals are markedly different, this means that the matter is worth investigating in a little bit more of a detail. So let's start by analyzing moderately fast turns. So here I wrote the equations of motion for the perturbations. These are the Mukhanov-Sasaki variables representing the perturbations. So from these we have those scalar fields which are more convenient to use. And the rate of the turn by an e-fold is represented by the rho parameter. So these are the equations of motion. So if we assume that the turn is moderately fast, by which I mean that k is the largest scale in the problem, rho is the second one, and all the other are smaller, then we can get we can derive approximate solutions for these equations. So this approximation of moderately fast turns applies to the model which was put forward by Gao, Langlois, and Mizuno. And in this model, without going into any details, there is a valley in the potential. The valley has very steep walls, and the valley suddenly turns. So the parameters of the potential are chosen so that the turn is by pi over 4, and the duration of the turn, by which I mean the amount of time that the field spends in the within fast changing potential, is as this fraction of the Hubble parameter, inverse. Sorry. So when we calculate numerically the power spectrum of the curvature perturbations, we get the following pattern. So here we have the calculated power spectrum of curvature perturbations normalized to the single field result, which is given here. And in this model, the Hubble parameter and the epsilon parameters stay almost constant, so it doesn't matter at which point they are evaluated. So we see that there are oscillations. The oscillations fall off as k to the power of -2, and the amplitude of those oscillations is proportional to the sharpness of the turn. So I'm going to be, as I said, I'm interested in the modes with the largest case. So we can easily see that even though that this turn is by a sizable angle, the value of the power spectrum for large case approaches the single field value without, without any shift as predicted in that paper. We can verify if the approximate solution that I had is correct or not. This is a slightly complicated plot. I'm showing this the evolution of just one mode of the of the perturbations. So here is the instantaneous total power spectrum of the curvature perturbations, and here is the power spectrum of the isocurvature perturbations. Those oscillating black lines show the modes which were initially the curvature perturbations and those induced. If they behaved according to my solutions, they should go as the sine and the cosine of the turning angle theta, and we see that the agreement is rather nice. They both go to 0.5, which is of course expected as the turning angle is pi over 4, and the small deviations can be traced back to the fact that there is a sudden change in the value of the mass parameter of the heavy field, which induces some additional oscillations. If the turn is very fast, then we should we should perhaps use the approximation put forward in that paper, worrying about a couple of technical details. So first, we have to remember that the two perturbations that we're considering are statistically independent. Second, we have to remember that only the first of these equations contains the time derivative of the rate of turning. And eventually, we have to worry that there are rho squared terms in this equation of motion. And if we want to represent the rate of turning by a delta function, of course, these are going to be troublesome. So, of course, there is a very nice technical way of going around it, and this is performing a field redefinition. And this is the field redefinition does a very nice thing. Mainly, it removes all the row square terms and removes the kinetic mixing. And if we only stick to the most singular terms in the equations of motion, we are left with those equations. So now, using the properties of the delta functions, it is easy to show when the solutions of the well behaved, in the sense that there is a finite jump in the derivatives, and this is these are the two independent solutions. However, I would like to stress that even if this might be a nice technical exercise, it is very challenging to build a full model which can be tested numerically, which I would love to do, because I mean this is the ultimate answer. However, if we consider the coupled equations that govern the evolution of various slower parameters, we see that the rate of turning is related to the mixed derivative of the potential, and then if that becomes large, a delta-like, without spoiling the slow roll, then of course we are again in trouble, because we have delta squared terms here. So in the realistic models, what we do, we introduce a very large features in the mass parameters for the perturbations. So it is exceedingly hard to have a realistic model which realizes the delta function. So my tentative summary of this preliminary result is this. So these are not all the examples that I checked, but all the examples that I saw show that the effects of subhorizon fast turns decouple, in the sense that they introduce features in the power spectrum. However, those features decay as a given power of the co-moving momentum. There are setups in which new effects are possible, but I think that the most interesting territory to test them is going to non-canonical kinetic terms, and of course this is work in progress. So I believe that I will have more to talk about in near future. Thank you.
Time for a few questions. How do you distinguish between the effects of these turns in multi-field space and just features in a single field scale potential, which also gives rise to this sort of like oscillations in the power spectrum?
So of course, this is notoriously difficult. This is what I chose to talk about large K limit, because of course the features that I showed, especially in this plot, can be traced back mainly to the variation of the mass parameters of the field. So in particular to the variation of the mass parameter of the curvature perturbation. That's right. I'm just thinking about this limit. I'm not saying anything about a functional form of this field. Of course, these people do, and this is a very interesting account.
So how do you stabilize the mass when you have such a fast? Can't I think of when you have such a fast turn, when you have to worry that you renormalize the mass and this field gets removed because it becomes very massive?
I think that the problem is the other way around. It can have a negative mass squared parameter. So I think that this is something which is phenomenologically more interesting. Of course, if it temporarily receives a large mass, it starts decaying. But of course, the decay is lasts only for a very short time, so it doesn't have a very big effect. So actually, yep. Okay.
But it decays exponentially, so even if it's a very short time.
Here, that's exponential.